Welcome back to physics. We're going to start by going over your homework from last night, so go ahead and have that out.
Okay, so a race car slows from 36 meters per second to 15 meters per second over 3 seconds. What is the average acceleration? So we take our final velocity, subtract our initial velocity, and then we divide by our total time. This gives me a negative 21 meters per second divided by 3.0 seconds. That gives me a negative 7.0 meters per second squared. A car is coasting backward downhill at a speed of 3.0 meters per second when the driver gets the engine started. After 2.5 seconds, the car is moving uphill 4.5 meters per second. If uphill is chosen as the positive direction, what is the car's average acceleration? What we need to do is we are defining uphill as positive. So my final velocity is the 4.5 meters per second. I'm going to subtract my initial velocity. Now, the initial velocity is coasting backwards downhill at a speed of 3 meters per second. So I need to be subtracting 3.0 meters per second. And then I'm going to divide by the total amount of time. So our time is a total of 2.5 seconds. So if I take and divide by 2.5 seconds, that gives me 7.5 meters per second divided by 2.5 seconds, which gives me an average of 3.0 meters per second squared. Number 9. A bus is moving at 25 meters per second when the driver steps on the brakes and brings the bus to a stop in 3 seconds. What is the average acceleration of the bus while braking? Well, our final velocity, since it is at a stop, is going to be 0. So I subtract my initial velocity, which is 25 meters per second, and I'm going to divide by the time of 3.0. So when we do that, we get a negative 8.3 repeating meters per second squared. I'm limited to 2 sig figs, so it's negative 8.3 meters per second. In part B, it says that the bus took twice as long to stop, so 6 seconds. How would the acceleration compare with what you found in part A? Now you might think that it'd be half as great. If you do the math, you will discover that it is exactly half. However, with sig figs, it is going to create a little bit of an issue. It's negative 4.16 repeating, so we're limited to 2 sig figs, so it would be 4.2 meters per second squared. And then number 10. Ron has been jogging to the bus stop for 2 minutes at 3.5 meters per second when he looks at his watch and sees that he has plenty of time before the bus arrives. Over the next 10 seconds, he slows his pace to a leisurely 0.75 meters per second. What was the average acceleration during this 10 seconds? Now, for part of this, there is extraneous information. It does not matter that he's been going for 2 minutes. The only time that we're concerned about is the 10-second period. As far as his change in speed, we see that he started at 3.5 and he was slowing down to 0.75. So if we take our final velocity of 0.75 meters per second and subtract our initial velocity of 3.5 meters per second, and then we're going to divide that by 10.0 seconds. When we do the subtraction, we get negative 2.75 meters per second, and then when we divide by 10 seconds, we get approximately negative 0.28 meters per second squared.
All right, we've been learning about acceleration in this chapter, and we learned the basic formula of acceleration is equal to the change in velocity over the change in time. Now, like many other algebraic equations, we can rearrange that formula to solve for other variables. So for instance, if you know the initial velocity, the acceleration, and the time of the acceleration, you could actually determine the final velocity by rearranging the formula. And we end up getting the final velocity equal to our initial velocity plus acceleration times time. The formula can be rearranged to find the initial velocity if you need to, or the time, or the acceleration if you know all the other individual parts. So let's take a look at problem number 18.
So we have a golf ball that's rolling up a hill toward a miniature golf hole. Assume that the direction toward the hole is positive. If the golf ball starts with a speed of 2 meters per second, but slows at a constant rate of a half a meter per second squared, what is its velocity after 2 seconds? So if we begin with our acceleration formula, we know that the acceleration is equal to my change in velocity, or my final velocity, minus my initial velocity, all over my change in time. Well, in this particular case, my acceleration is going to be a negative 0.50 meters per second squared because it is slowing down. Therefore, acceleration is going against the direction of motion, and the direction of motion is considered positive. So anything going against it would then be considered negative. Then what I can do is I can set that equal to my final velocity, which I don't know, minus my initial velocity. My initial velocity is 2.0 meters per second, and then my change in time is 2 seconds. Using some algebra, I can multiply both sides by 2, and it gives me 2 seconds. That gives me a negative 1.0 meters per second is equal to the velocity minus 2.0 meters per second. By adding 2.0 meters per second to both sides, I get my final velocity being equal to 1.0 meters per second. What is the golf ball's velocity if the constant acceleration continues for 6 seconds? Alright, so once again, we'll start off with our formula. I'll go ahead and substitute in the values that we know. So I have a negative 0.50 meters per second squared. That is equal to my final velocity minus my initial velocity over my time of 6 seconds. I'm going to multiply both sides by 6 seconds. That gives me a negative 3.0 meters per second equal to my velocity minus 2.0 meters per second. If I add 2 meters per second, I get my final velocity in this scenario as being a negative 1.0 meters per second, which means the ball is moving back toward the direction from which it came. And then describe the motion of the golf ball in words and with a motion diagram. We're just going to skip that one.
So we've been looking at acceleration and velocity. We've studied position time graphs and velocity time graphs. One thing that we do need to understand is a very simple concept, one that you acknowledge already in your mind. But sometimes when we start working out problems, we forget and we do things that we normally wouldn't do. And that is the position as we have acceleration. We all understand that if I start in a car and I start accelerating, in the first second I may only travel 5 meters. However, if I'm continuing to accelerate, then the next second I'm going to travel a further distance. And then the next second I'll travel further. So each time period we are increasing the distance or even the amount of distance that is changed with each successive time interval. It's a very simple concept, but sometimes when we get into the problems, we forget that. So as a vehicle accelerates, it will travel further distance in one time frame than it did in the previous time frame, if, of course, the acceleration is positive. What that's going to do to our position time graph is it's going to create a curve, kind of a parabola type of look or a hyperbola type of look if we were to continue on in that acceleration. So here you can see a graphic, the position time graph for a car that's going on a constant acceleration. You can see that that green curve there is steadily going up and it's getting steeper and steeper. Those red lines are 2 points in which they figured out what is the instantaneous acceleration at that position. Remember, in order to find the instantaneous acceleration given a graph, you have to use the tangent line and then figure out what the slope of that tangent line is. The area under a velocity time graph is going to be equal to the total displacement of that vehicle. So as we look at the displacement, we can see that they are increasing the amount of distance that they're traveling in each successive time frame. But what is the total distance that they have traveled? In order to do that, we have to find the area underneath the curve. Now, in order to do that, you have to use some calculus. But this is an algebra-based physics class, so we're not going to deal with curves. We're going to deal more with shapes that we can figure out the areas under, and we may need to break them down into different pieces. So let's take a look at example problem number 3. It says the velocity time graph shows the motion of an airplane. Find the displacement of the airplane at t equals 1 second, and then when time is equal to 2 seconds. So in order to find the total displacement, we have to find the area under the curve. It looks as though that this airplane is traveling at 75 meters per second. And so during that 1 second interval, I would take the base of 1 times the height of 75, and that would give me a total of 75 meters. At the 2 second mark, if I take the base, which is now 2, times the height, which is 75, that gives me 150 meters. So let's try problem number 22.
In the figure, determine the velocity of an airplane that is speeding up at each of the following times. So at 1 second, I look at my graph and I see that at 1 second, my airplane is traveling about 74 meters per second. After 2 seconds, going up, we see that it is traveling about 78 meters per second. And in 3 seconds, it's all the way up here at roughly 82 meters per second. Number 25 says a car is driven at a constant velocity of 25 meters per second for 10 minutes. The car runs out of gas and the driver walks in the same direction at 1.5 meters per second for 20 minutes to the nearest gas station. The driver takes 2 minutes to fill a gasoline can, then walks back to the car at 1.2 meters per second, and eventually drives home at 25 meters per second in the direction opposite that of the original trip. Draw a velocity time graph using seconds as your time unit, and then calculate the distance the driver walked to the gas station to find the time it took him to walk back to the car. And then part B, we're wanting to draw a position time graph for the situation using the areas under the velocity time graph. So we're wanting a velocity time graph using seconds as our unit of time. This is a very long process because he traveled for 10 minutes and then walked for 20 minutes, stood still for 2 minutes, and then he walked back to the car, but we don't know what time that was, and then he eventually drives home at 25 meters per second in the direction opposite that of the original trip until he gets home, so that's going to be another 10 minutes there. So we've got a good amount of time that we need to take into account. So we have 10 minutes, which is 600 seconds. Then I've got 20 minutes that he's walking. That would give me 1200 seconds. And then 2 minutes, which is another 120 seconds. And then he walks back to his car traveling at a different speed. So I don't know what that time is. But then the time it takes him to get home once he's back in his vehicle is another 10 minutes, so 600 seconds there. So I need to figure out this missing time frame first. So to do that, I need to figure out, well, how far did he go? What was the distance? Distance is equal to rate times time. He walked for 1.5 meters per second, and he did that for 20 minutes, or 1200 seconds. So that gives me 1800 meters. That means when he travels back to his vehicle, he has to travel the same 1800 meters, but now he's traveling at 1.2 meters per second for an undisclosed amount of time. So if I divide both sides by 1.2, I get the time being 1500 seconds. So the total amount of time it took him was 4020 seconds. Now that I know the time, I can draw my velocity time graph. So down here is my time, and they want me to do it in seconds. All the way over here is 4020. So this is roughly 2000, 1000. Now, as far as my velocity, my highest is going to be 25 meters per second. Okay, so the car is driven constantly 25 meters per second for 10 minutes, or 600 seconds. I'm going to draw this to be roughly at the 600 mark. The car runs out of gas, and the driver walks the same direction at 1.5 meters per second for 20 minutes. So 1.5 meters per second would be over here. And we are doing this for 1200 seconds. So that put me at 1800 seconds. Driver takes 2 minutes to fill the gas can. So that's another 120 seconds. So we're at a zero velocity during that time. Then he walks back to the car at 1.5 meters per second and eventually drives home. So now that he's walking back, he is going to have a negative velocity. So I should have done this a little bit differently and allowed myself some negatives. So we're going to go down at 1.2, and he does that for 1500 seconds. And then he's going to drive home at 25 meters per second in the direction opposite the original trip. So we would have to go all the way down to negative 25 until we reach the end result here. Okay, so in part A it says calculate the distance the driver walked to the gas station, find the time it took him to walk back to the car. Well, we did that already over here. He walked 1800 meters to the gas station, and it took him 1500 seconds to walk back. And then draw a position time graph for the situation using the areas under the velocity time graph. So, a position time graph then, we would need to draw. So initially we're going to go up quite a bit, and then it's going to steadily climb, but at a lower rate. Then for the next 2 minutes it's going to stay constant, and then we're going to decline slowly, and then we're going to be rapidly driving away. So it's going to look something like that. I didn't take the time to do each individual piece there, but you get the idea of the basic form that it's going to have. Mini graphs have to be broken down into smaller sections in order to really figure out what the total distance is. So for instance, on the screen you see that I've got a velocity time graph where I can break it up into a rectangle and a triangle. Now let's take a look at the triangle. If we find the area of a triangle, we know its area is equal to 1/2 the base times the height. Now in this particular case, the base is this change in time, and the height is my change in velocity. Since my change in velocity is equal to acceleration times the change in time, what I can do is I can substitute in. So instead of this change in velocity, I can substitute in this amount. So if I rewrite this formula, I have 1/2 my change in time, or I'll just use t for time, times my change in velocity. Well, what is that change in velocity? That is acceleration times change in time again, which ends up giving me a formula that is 1/2 a t squared, because I already have two t's going on. So I've got this change in time and this change in time, so that gives me t squared. To find the area of the rectangle, that would just simply be base times height. Again, the base is my change in time, my height is change in velocity, and so when I work that out, I have delta t times my initial velocity, because it didn't change at all. Combining these two together gives me the area times the change in time times the velocity plus 1/2 acceleration times the change in time squared. When I simplify that down, since the area is giving me the distance, then my final distance is equal to whatever my initial distance is, plus my initial velocity times time, plus 1/2 at squared. This formula right here is one of your basic formulas that you have in Chapter 3, and we will use it a lot. But this is how it was derived, all of this.